Okay, welcome everyone back to the class. So in this lecture, we can focus to the new topics, the nature of light and the wave optic. Okay, so in the course syllabus, it said that we're gonna focus on the interference and also diffraction. So it's another set of the slide. However, on the way that we're going, sometimes we need to go back to the ray optics. So when we're talking about the reflection and the refractions, when we need the basic from that topics, I will review it again. Okay, but not for these videos. So let's look in overall what we're gonna discuss. So first is how to measure the speed of light. This is a story on how things is working, how people in the past was measure the speed of light. We introduce you about what is ray optic and what is a wave optics. Okay. Then we're talking about the Huygens principles. And after that, we're gonna do the double slits experiments, interference, and talking about the intensities. However, in these lectures, these three topics will not be aligned in this list of the topics. But I maybe start with the intensity first, just to starting from what you have learned before, okay, and leads that to the result of the double slit experiments, and then we're talking about the Young. So the Young experiments come at the end. Okay. However, as mentioned before, whatever direction of the topic is, at the end you will get the same, just presenting a different point of view so that you see how things is evolving. This is, I think, what I think it's better. But if you prefer, following the topic as it's written here, you can following the books. That it's you will get exactly the same. Okay. And then for the second video, we're gonna talking about the change of the phase due to the reflections, interference in the thin films, and the Michelson interferometers. Since the topic including the reflection, so maybe I need to review you a bit about reflection, diffractions. Okay, that's you have learned before in the high schools. Okay, so let's start. So how to measure the speed of light? Starting from the periods of the Galileo. So in that time, he did several things. Measuring the speed of light is also one of his work. In that time, what he used the lamp. Okay, so and then there has his colleague there far away, and then we turn on when he let's say turn on the lamp. So shutter, open the shutters, the light go to his colleague, and then when his colleague see the light, he open the shutter of his side, and then Galileo will see the light from another side, and then he use pulse to try to measure the time. Okay. But it doesn't work because the light is too fast. So what he get is basically the response for him that after you see the light and the body respond, to trigger everything, and then you think that okay, now we got the traveling time of light. Okay, so it didn't work. So the first measurements of the speed of light coming from Romer. So he was the astronaut. Yeah. So he worked in the observatory at Paris in that time. So he tried to recording. At the beginning, he didn't expect to measure the speed of light. What he did is basically something from Galileo also. Galileo have released one work, scientific works based on the observation he made through the telescope, and in that paper, this one, they also mentioned about the Medicean star. It's what we call later the Galilean moons. Okay, so this is the moon that appearing to circle around Jupiter's. Okay, so the moon name is Io, and the second one is Europa, and there is another two I cannot remember. So what Romer tried to do is basically recording the time of the eclipse. So when the moons disappear, okay, and the moon appear, okay, so he tried to figure the periods. Okay, so when the moon disappear, so this is the periods, and then after that when the moon start to appear. Okay, and as you know that the earth is rotate, okay, and so the distance that's light traveling from the Jupiter to the earth, it's there are difference. Okay, the distance that the light traveling is different. Romer start to see the deviation on that. Okay, however, he didn't rely that, okay, this is the way to measure the speed of light, following by his work. So who did calculate? It's Christian Huygens. So he used the Romer table, let's say, the data that Romer collect, and try to calculate back the speed of light. So in that time, in that period, they have some knowledge of to estimate let's say the distance that Earth circulate around the sun. Okay, so use that number, calculate back, so he get the speed of light. I think I'm not sure that it deviates by 20 or 30% of the today numbers. Okay, I'm not sure that it's greater or it's less. Okay, but it's nice. I mean, following the work that they have done, so that it's open the probability to measure that. Okay, and then the way to the new method to measure the speed of light using the interferometers, several things happen after that. Okay, so that is kind of histories of how this thing is work in the past. Okay, so now we know that the light it's not in that, I mean it's something that have the speed limits, and this is what they are trying to measure. Okay, so let's see what we need to discuss next. We are talking about the ray optics and the wave optics. Okay, so this is starting from the principle that when you have the wave traveling through the open apertures, okay, it can be the water wave that passing through the harbors, or the canals going outside, for example, or from outside go to inside. Or we can talk about the light traveling to the tunnel, to the open aperture like this. Okay, so if the aperture is really big compared to the wavelength of the light, that we're gonna see today at the end of the class, that how the light how the wavelength of the light is measured. So if the lambda is much less than the size of the apertures, so the ray will go straight. So it's like you have the light turn on, and then just the light traveling like this. So what you see on the screen, it's exactly the same size of what you have, what it passed through these apertures. Okay, but then when the aperture is when very small, so in order roughly to the wavelength, you start to see that the rays spread out when it passing to the open apertures. Okay, and then when the size of the aperture is much smaller than the wavelength, okay, so the aperture start to become a point source, and then a point source can emit the spherical wave. Okay, so this is a case that we are discussing as of today. So in the case that D is much greater than lambda, this is the ray optics. Okay, and in the case that the size is comparable, this is the wave optic. Okay, and we need to use the wave phenomena to describe this phenomena we have seen. Okay. Before we start, we need one principle that we need it at the end, maybe in the diffractions. It's called the Huygens principles. So the Huygens principles say that all points on a given wavefront are taken as a point source for the productions of this spherical secondary wave called a wavelet. Okay, so what he means is basically, so you have the wavefronts. So every point at this front can create the spherical wave. Okay, so the point source itself, the point source start to become, the position on the wavefront become a point source to the secondary wave. And then when you have the secondary wave, all the point source on the secondary wave also become the point source for the tertiary wave, and so on and so forth. Okay. So after some times the interval have passed, the new position of the wavefront is a surface tangent to the wavelet. Okay, so you see that when the lights come in this way, the wavefront start to be, this is the wavefront, it is gone. But to describe these wavefronts with the Huygens principle, you need to make the tangent surface. Okay, so that is what he said. Okay, so the wavefront that's come from this one to this one, it still be the same wavefronts as before. Okay, if it's spherical also. So the same. Okay, just make that. So that the concept of the wavefronts will not change. So it's if the wave is traveling. Okay, what changed is basically just to say that you can consider that all points on the wavefront are the source of the secondary wave productions. Okay, this is the nature of light. There is a topic of the reflection and refractions with the ray optic that I will discuss that if it's needed. Okay, I just need to review a bit with the theme of the lectures because it's not written in the course syllabus. Okay, however, if it's needed, for example, in the next video, we're talking about the reflections, the phase change during the due to the refractions, so that maybe it's better to review it a bit so that you can have an idea of the reflections. Okay, wave equation, wave function, and the intensities. As mentioned in this lecture, I will not follow the book by order, but at the end you will get exactly the same solution as written in the book. But I prefer to start from something that you have learned before. Okay, so we consider the following situations and we try to describe by using the wave equation, wave function, and definition of the intensity we have discussed before. So starting from the wave fronts, okay, you have the wave traveling to the apertures, to open apertures like this. Okay, let's consider the first one here. Okay, so you have the light somewhere here. So this is the intensity, so what you see on the screen. Okay, it's not that going to that direction. Okay, just saying that the intensity you see, it's large in the middle. Okay, so this is what you see, maybe like this. Okay, and then from the second source, you're gonna be the same like this. Okay, so if you try to say you open both 1 and 2, so basically this is what you can imagine, that you're gonna have something start to go big. Okay, and then it's go like this. So this is the include, this is just 1 and 2 open together. Okay, so this is your idea. Okay, if nothing changed, no conception, no wrong conception, so this is what you should expect, right? However, this is not what you will see. Okay, this is something that's not true. Okay, what you see, it's basically, it's like a patterns of intensity. So you're gonna have like this. This is what you observe. Okay, this is what you can observe. So the strand is that at some point, for example, maybe this one, I not draw it, I mean, with exact scale or which position it's gonna happen, just an ideas. Okay, at these positions, when you turn on 1 or 2, you see the light. But when you turn on 1 and 2, you do not see the light. Okay, so this is something different, right? I mean, it's something that cannot be just add up immediately. Okay, something need to be need to bring to the to your considerations. Okay, so what we gonna do is we're starting to what you have learned before in the actually in the last lectures. You start to learn that from the first semester, but in the last lecture you also learned that it's about the wave, right? So you the wave equation. So starting from the wave equations, if I can find the space. Okay, that's maybe I clean up this thing a bit. No, they're not needed. Just keep it there. So consider the wave equation. The second derivative of x of y. So you have the wave function yxt, right? And the second derivative with respect to t. This is the wave equation. Right. This is wave equations. So what is y? Y is the wave function, right? Which can be, if it's a string wave, it's y say that how deviate it's from the equilibrium, right? It can be E or B, right? It can be E or B. It can be compression and decompression of the sound wave, compression and decompression of the sound wave. Okay. So it can be, let's say that it's deviation from the equilibriums. When you have the wave, you disturb it, it starts to vibrate, and that's something that off from the equilibriums. It's what we call the wave functions, or the y in this case. Okay. I think in the maybe we can introduce it here. We're gonna do it again in the quantum mechanics. So when we write the wave functions, people usually write a symbol psi. Okay, so this is the wave function. So you can write y if you prefer, but for me, you can write it psi. It's the same. Okay. So okay, you have here. Okay. Then we are talking about the property of the wave function first. Okay. Why we need to discuss about the property of the wave function? Because we are talking about the situation that you have the wave from the point source 1 and then the wave from the point source 2. Then when you turn it on together, the wave function need to be add up. Okay. So first is that the wave equation, it's linear equations. Okay. Where should I put it? Okay, that's right here. It's linear equations. Okay. What linear equation mean? It mean when you have the solutions and then you would like to have another solution, for example, 10 times bigger, you multiply it by any constants. That constant that you multiply, so the new function, which is constant times the old function, it still be the solution for the wave equations. And then also if you have the function 1 as an equation solution, function 2 as a solution, function of 1 and 2 to sum the function of 1 and 2 together, it still be the solutions. Okay. So what I'm trying to say is, for example, you have the oops, sorry. You have so this is y minus 1 over v square, e square of y equal to 0, and this is y1 or phi1, sorry. Okay, phi1 corresponding to this one. Okay, and then you have the second derivative, the second equations of psi 2, okay, which corresponding to this one. Okay, so when you turn it on, so you sum it up together, you're gonna see that the equations that you have over phi1 plus psi 2, it still becomes 0. So you have another solution, which is the sum of wave function, the first and the second one. Okay. You can also multiply by any number, any constant, which is the same. Okay, so you multiply by c, it still be 0. You multiply by c prime, the second equation still becomes 0. So that is the way you form. Okay. So this is the first thing. The second one is the definition of what we call the intensities. Okay. Intensity is basically proportional to the wave function square, because we need to measure the intensities. It's the what you see, it's energy that you're trying to detect. Okay, so it's depend on the wave function squares. Okay, the wave function itself, we never say that the wave function needs to be positive. No one say that. It can be negative. It can even be the complex numbers that you're gonna see in the quantum class lectures. So it can be everything. Okay, However, the intensity is something that we measure. It needs to be real. It needs to be positive. It represents the intensity of the light that you see on the screen, okay, or something that detect the energy in that specific positions, okay. So it needs to be real. It needs to be positive. So what you see is basically the intensity when you turn on both. I should maybe use another color so it can contrast with the blue one powder. So we are talking about the intensity of psi 1 and psi 2. The color is not that good. So it's proportional to the psi 1 plus psi 2 square. Okay. So psi 1 plus psi 2 square is what? It's psi 1 square plus psi 2 square plus 2 psi 1 psi 2. Okay. Psi 1 square is the I1. Psi 2 square is I2. This is new. Okay. This is addition. This is added to the term. So you can really see that now when you turn on two light, it's not just the sum of the intensity from both sources, but it's also having it also has another position, another term, another factors, another term that come into our considerations. Okay, and this term can be positive, it can be negative also. Can it be complex number? No, it cannot be a complex numbers, okay, because if it's complex number, you cannot really measure that. Okay, from that definitions, to psi 1, psi 2 cannot be a complex number. Okay? And then maybe if you ask, okay, but if psi is complex, so basically if psi is complex, when you try to measure the intensity, it's become psi star psi. So this is the complex conjugate. Okay, so you have the complex number multiplied by the complex conjugate. You're gonna get the real numbers. Okay, so this is definition that we're gonna use in quantum mechanics. But for this, wave things, you can also use this one. Okay, but it's basically the same. Okay, so now you see that reasons that why you see some dark spot here. Okay, some position that if you just turn on one light, you see that you see the light there, but then you turn on two, you don't see the light in that positions. Okay, because of this term. Okay, so maybe you start to see that why I try to describe this topic in this way first, because this is starting from something that you have learned before. Okay, you learn about the intensity in the last lectures. You learn about the wave equation already. Turn on two light, it's in you have two wave functions, and the sum need to satisfy the wave equation also. Okay, and then you calculate something that you can measure, which is the intensities. Okay, so now you start with two waves with the following wave equations using the superposition principle, and what will you get? Okay, it can be psi, it can be cosine, it can be even complex number, and then you take the real part of that. Whatever you like. Okay, I use psi because it's gonna get the same, exactly the same answer in the survey. Okay, but if you would like to do cos, it's totally fine. Okay, it's exactly the same. So you take phi 1 plus phi 2, so it's become a psi omega t plus phi, or it can be psi omega t plus psi omega t plus phi. Okay, And then what you learn from the trigonometry is that psi A plus psi B equal to 2 psi A plus B over 2 cosine A minus B over 2. So you put, okay, so you put it back. So it's 2A of psi A plus B. So this is A, this is B. So plus become 2 omega t plus phi divided by 2. So it's become omega t plus phi over 2. Okay. And then minus 1 is cosine minus phi over 2. Cosine minus is cosine. Okay. So you get cosine phi over 2. Okay. So if I just switch these two terms just to make easy form that you can have a look, it's become 2a cosine phi over 2 psi omega t plus phi over 2. Okay, so in this form you see that the first one, it's not a time dependent. Okay, this is not, it's time independent. Let's say maybe it's the right word to do to write. Time independent. Okay, when it's time independent, it will not represent the wave, right? It's present prefactors, it present the amplitude of the wave, and the second term is the waveform. Okay, and you see that the wave itself can have the same angular frequency. Okay, you start with omega t. Okay, but what is different is that this is the wave. What is different is the same first, so the same angular frequency. What is different? It's the phase. Okay, so this is the phase phi over 2, which is basically half of the phase difference of wave function 1 and the wave function 2. Okay, so now you have this one. Then if you would like to do the intensities, okay, maybe use the blue one. So intensity is basically 4a squared cosine square of phi over 2 psi omega 2 omega t plus phi over 2 square. Okay, and then when you detect the light intensity, it's average on time. Okay, it's not instantaneous, it's average on time. So you get the expectation. So whatever you get, it's just one number and then cosine square phi over 2. Okay, and in this one, so we call it the Imax, so the maximums, and then cosine over 2, you average on this, it's the average of that is 1 over 2. Okay, so this is the intensity you will get. Okay, and what you see is that basically the intensity, it's not depend on the position of the wave. Okay, what it's depend, it's basically depend on the phase difference only, and that's it. And the phase difference, it's coming from the source itself. So if you have two sources with the exactly with the difference of the phase, there is a phase difference, and that is a factor that controls the intensities. Okay, you will see the result of this one later. Okay, so now you have the tools of this one, so you can do the superposition of two waves. Okay, so now let's try to do it in the interference way when you have two slits and you have the light traveling. Okay, so we're gonna use basically this one, and later we're gonna use the intensity for that. Okay, let's start with the wave interference. So we consider that you have the first wave coming from the source 1. It's traveling with a distance r1. You have the source number 2, which give you the wave phi 2. Okay, this is the wave. When this wave reach this point, this thing become source of the secondary wave. As a Huygens principle, it's produce the wave. Okay, it's wave traveling to the screen at point P. The distance that S1 to P and S2 to P is basically the same plus the small difference called the delta. Okay. So what you have is basically R2 is, sorry, it should be not the vector, it's R2 equal to the R1 plus the delta. Okay, this is what you have seen. You don't need to look at the this one yet, so we can see it later. Okay, so now you can write the wave functions. So maybe I move this one a bit up. So you write the wave functions. So phi 1 equal to the whatever amplitude, it psi equals psi whatever, kx minus omega t, right? But this traveling in the r direction, so just write the general form. So kr minus the omega t. Okay, and then you have psi 2, which is a psi k r2, right? K r2 is I give r1 equal to r, so kr plus k delta minus the omega t. Okay, because it's kr2, right? This is kr2, and r2 is r plus the delta. So you have this one. So the same, you try to sum it. Okay. Do it in the same way. So you get 2a, just the same. What you're gonna get is that you're gonna have the term of the psi, which is the waveform. Okay, I keep it here. This present the wave, and you're gonna have cosine of you take it minus, and then it's become k delta over 2. Okay, so this is the amplitude. Okay, this is the wave. Okay, so you have this one. We don't need to talking about the wave. Okay, we can just looking at the amplitude. So because what we would like to do is try to understand the point where we're gonna have the bright light or the dark. Okay, and we try to do that from this one. So when you're talking about the dark, so it's mean that intensity becomes 0. So what really control things is cosine. Okay, 2a, if 2a is 0, it's 0 everywhere, so you don't really need to talk about that, because if a is 0, it's basically you have no wave in these problems. Okay, so 2a can be any arbitrary numbers as you prefer, but what's control the light at the screen, on the screen, that it's going to be bright, it's going to be dark, it's cosine k delta over 2. Okay, so if you consider the bright case. If you consider the bright case, what it means? It means that k delta over 2 need to become 0. Cosine 0 is 1, right? It should be, can be pi over 2? No, it cannot, because cosine pi over 2 is 0, right? So it's become pi, but it can be plus and minus pi, plus and minus 2 pi, and go on and so on. Okay. And on the dark mode, so you're gonna get k delta over 2 become plus and minus pi over 2, plus and minus 3 pi over 2, plus and minus 5 pi over 2, and so on. Okay, so this is what you will get from the equations. You can see that up to this point, we never talk about the Young experiment at all, right? We use just the wave equation and try to solve it, okay? And then what you can do next is basically put the k back, so you know that k is 2 pi over lambda, right? So what you have basically, maybe I cancel this term 2, okay? Pi can be deleted, cancel. 0 is 0 pi, so to cancel that. So what you will get is basically delta over you take the delta, so delta equal to 0 plus and minus lambda plus and minus 2 lambda and so on. And in this case, delta gonna equal plus and minus lambda over 2 plus and minus 3 lambda over 2 plus and minus 5 lambda over 2 and so on. Okay, so this is the solution we're gonna have. So you know that the light need to be traveling from the second source, which more distant than the first source in unit of lambda. So if it's lambda, you're gonna get the bright situation, the bright case. If it's half of the lambda, so the wave gonna cancel, and you're gonna have the dark fringe. Okay, dark in on the screen. Okay. So this is what you will get on the this is what you will get from the analysis model of the wave interference topic. Okay. So now we go next to the double slit experiments. So we just continue this one, but doing a little more detail on the measurements. Okay. So if we assume that the L is much larger than the size between two apertures, L is larger than D. Okay. What the model is that when in that case, so starting from source number 1, it's going to the point you interested in, and from number 2 to point 2 you interested in, with the difference delta, so the size is R1 minus R2, and if the source is too far, you can just like cutting here, and then you use the d sine theta to become a delta. Okay, and then if you trying to measure from the center, so between two sources, okay, so you draw the line from the center from the center of the source of the slit to the center of the screen. It's the length L. Okay, and then you're talking about the position Y. So this is position that you may observe the dark fringe or the bright. Okay. So the angle that we are talking here, theta, it's gonna be the same, approximately the same as here. Okay. So this is kind of the approximations. I think you can just do it. Maybe let's try to make it. So you have maybe I should, if I zoom, I just try to draw it. Let's find a place to do like here. Okay, so you have this S1 and S2. So this is starting from, this is theta. This is the middle point. Okay, this thing go here, and this thing go here. Okay. So let's start from the normal case and then we treat it later. Okay. So what you're gonna have is basically, this is theta, right? We approximate, this is very far, so that so this is, okay, so this angle equal to this angle is opposite angle, this one is opposite to this one. Okay, and this is diagonal, right? So what you have is basically this thing. It's become 180 minus 90 minus theta, right? So it's become 90 minus theta. Okay, and then you consider this a small triangular here. So you need to find this one. So the angle you would like to find, plus x plus 90 minus theta equal to 180. Okay, so what the angle you are talking about here is basically 100 minus 80 plus theta minus 90 minus x. Okay, so this is 90, so it's theta plus 90 minus x. Okay, and then if we treat that this is a very long situation where L is very long, so we treat x equal to 90, so the angle we consider is theta. Okay, so now when you have the theta here, right, you can see that from the trigonometry relation, you see that the tan theta, it's become y over L. Okay, and then what you have is delta, before it's d sine theta, right? So you have d sine theta equal to the m lambda, for example. This is for the bright, and d sine theta for the dark equal to the m plus half of the lambda. This is bright, this is dark. Okay. So when the screen is very far, you do the small angle approximations. Small angle approximation. Okay, so sine theta b, it's gonna become tan theta b, right? This side become tan. So what you're gonna have is dy over L equal to the m lambda, or you arrange it. you get y equal to the L lambda over D and M. Okay, so this is the same. You're gonna have y equal to the L lambda over D M plus half. Okay, this is for dark fringe, this is for bright. Okay, so what you have from here is now you have the way to measure the wavelength. Okay, why? Because when you do the experiment, right, you have the double slit like this one, you try to find the position of the dark or the bright, you measure it, okay, and then you count the order. So the center, it's m equal to 0, shift to m1, m equal to 2, m equal to 3, okay. So now you have the relation of y equal to the slope times x, right, where y is y bright or dark, x is basically m, okay. So the slope is the L lambda over D, okay. So when you do the this is y bright, this is m, so m is 0, 1, 2, 3, whatever, you make the plot, you measure the slope, so the slope become L lambda over 2 over D, right? So finally you have lambda equal to the D times slope divided by L. Okay, so this is the this is the way to measure the wavelength. Okay, you can use also the dark one. That is fine. Okay, so this is the result of the experiments, and we call this one Young double slit experiments. Okay, so you can see that even you don't know what is Young double slit experiment is, you can start from the wave superpositions, wave functions, try to sum it, describe the phenomenons, and then you get it out. You get it right here. Okay. So when you if you read the book, so the book will start from this one and go back in this direction. Okay. I'm just do it in the opposite way. Okay. Great. So now you can measure the wavelength of the light. Okay, for the last page, the light intensity for the double slit interference, since it's every class is online, it's difficult to demonstrate to you from here. So I put the link to the interactive learning so that you can play around, so you get the idea of the interference. Okay, you turn on one light source, you turn on a different light source. Okay. Yeah, so like this one, you have the light generators. I don't like this one much because basically I would like to have two sources, and yeah, but that's fine. I mean, it can represent here the two sources, right? So this is the source from the slit, and then when you have a screen, okay. But what you can really see from here is the intensities. You see that the intensity is basically roughly the same for all the bright you have seen. Okay, why this is the case? Okay, let's stop one underneath graph. Okay, turn on 2. Let's see a bit. So you start to see the intensity. Okay. Why intensity is roughly the same? This is because what you have calculated before. The intensities here equal to the Imax cosine of 5/2, right? So it's depend on the phi. Okay, so it's depend on the phase difference. Okay, so it's depend on the difference between two source and traveling. So this is what we see the difference. Okay, so if you adjust the separations, you're gonna see the difference. Yeah, it maybe cannot really see from here. It's yeah, it cannot really see clearly from here, but what you can see, it's basically what you get. You have the same intensities. Okay, so this is what I trying to talk. This is what I mean. Okay, so you don't really see this the slowing down of the intensities when it's spread. Okay, in the central regions, you still see the center in the central region, and off from the central, you still see the difference. The same intensities. Okay, so this is the intensity of the double slit interference patterns. Okay, so this is what we have learned today. Okay, so we basically cover of how to measure the speed of light. We're talking about the ray optic. Okay, we're talking about the Huygens principles, and then we're talking about the intensities, wave interference, and the Young double slit experiments. So the next video, we're gonna talking about the remaining topics. And as I say, since we touched the reflection, maybe I will need to make a short review for that first. Okay, so that you can have an ideas and can continue the class. Okay. Okay, so this is the lecture of today. So this lecture is expect to be on Monday of 21st, and then on Wednesday we're gonna have the live tutorials. But the tutorials topics gonna be the electromagnetic wave. Okay, so try to finish that first, and also try to finish this one so that keep momentum of your studyings. And if you have any questions, just feel free to post it on Facebook or sending by email, and I will answer that. Okay, so I think this is all from today. So we used roughly 1 hour, which is great. Okay, see you next time. Bye bye.